Okay, so we're going to look at several examples on how to analytically find answers to limit questions. Our first question here asks us to find the limit of 3 as x approaches 2. Well, with limits, you always just want to do direct substitution first, and unless you get a 0 over 0, or you end up dividing by 0, your answer is just going to be flat out whatever number you get out. So if I were to plug x equals 2 into 3, nothing happens. There is no x, so my answer is just 3. Um, Here, the limit of x as x approaches -4, well, if I plug in -4 in, I'm going to get -4 out, which is fine. As long as I get a number, that is my answer. The limit of x squared as x approaches 2. Again, I'm going to take my 2, plug it in, so I'm going to get 2 squared, and that's going to be 4. So these are just simple answers. So first thing you want to ever try to do is just plug it in and see what happens. If you get 0 over 0, or you're dividing by 0, then you might have to take a little bit more of a look, but this is the first step. So make it a little more complicated. If I'm looking to find the limit as 4x squared plus 3 as x approaches 2, what I need to do is plug my number in. So I'm going to get 4 times 2 squared plus 3. That's going to be 4 times 4 plus 3, which is going to be 16 plus 3, or simply 19. We get an answer of 19. That's our limit. We are done. So the limit of a rational function. Just because it's rational doesn't mean it's going to be anything weird. We want to always try and plug the number in first. So the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. We want to see what happens when we plug 1 in. So we're going to get 1 squared plus 1 plus 2 over 1 plus 1. And that's going to give us 1 plus 1 plus 2, which is going to be 4 over 2, which just gives us an answer of 2. And that is our limit. As long as we get a number, we are good to go. Now for trig functions, it's the same way, but we have to evaluate whatever the function is at that particular angle. So we're given an angle of 0, pi, and 0. So we will show you how this works. For tangent, I always think it's best to break it down into sine and cosine. So this is the same thing as the tangent of 0, which is the sine of 0 over the cosine of 0. The sine of 0 is 0. The cosine of 0 is 1. And so we're finally left with an answer of 0. So that is the value of tangent at an angle of 0. And since we're not dividing by 0, we didn't get 0 over 0, we are good to go. So this is our answer. So now we see like the limit as x approaches pi of the cosine of x. Well, this is just going to be, this is just going to be the cosine of pi, which the cosine of pi is just -1. So we get an answer. We're good to go here. And then we have the limit as x approaches 0 of sine squared of x. So this is going to be the same thing as the sine squared of 0, because we're just directly substituting in here. Well, the sine of 0 is 0. Now, we have to remember to square this answer, because we are squaring what the sine of 0 is, which just ends up being 0. So if there's a trig function, again, just directly substitute and use what you know about the unit circle to find our answer. Now we have some special circumstances that require a little bit more work. If we start off and we do what we have done in the past, we're going to start by plugging our number in. So we're going to get 1 squared plus 1 minus 2 over 1 minus 1, which if you do this math, you will see that we have 0 over 0. We call this the indeterminate form, which means there's nothing we can say about it. What you need to think about when you see this is that when we plug 1 in to our numerator, we get a 0. When we plug 1 into our denominator, we get a 0. That means that is a factor, that 1 is a 0 of both the numerator and denominator. So we can likely factor something out to actually simplify this function here to get ourselves a better answer. So what we're going to do is we are going to check and see what kind of factors we have in our numerator. So we are going to factor. Now, if I factor the numerator, I'm going to set up my brackets. I know I have an x squared, so my first terms are going to both be x's. I now have to figure out two terms that multiply to make negative 2 that add to make a positive 1. Well, there's different options that I can choose from, but if I need to add to make a positive 1, I need to have one number that is bigger than the other. So I'm going to be left with a positive 2 and a minus 1. That's how this would factor. And as you can see, our x to the negative 1, this 0, this exists as a factor of the numerator. That's why this happened. This happened because x minus 1 was not only in the denominator, but it's also a factor of the numerator. That's why we got this 0 over 0. So at this point, our entire denominator is x minus 1. We have a factor on top, so we can actually eliminate this. So we get x plus 2. So our big limit up at the top is the same thing as the limit as x approaches 1 of x plus 2. Which now, because we're not in danger of dividing by 0, we can plug our 1 in. So we're going to get 1 plus 2, which gives us 3. So in the case that you get a 0 over 0, you're going to want to choose some strategies. The dividing out strategy is one that you'll use mainly when you have some rational functions like this. Our next example is called the rationalizing technique. Again, you're going to start off exactly the same as we have before by plugging in these numbers. Plugging in 0 in to see what you get. So you're going to get the square root of 0 plus 1 minus 1 over 0, which this is 1 minus 1 over 0, which is 0 over 0. So again, we get the indeterminate form. So now we're going to have to do a little bit more work. The rationalizing technique is different, and is different than what we did before, because not only are we going to divide out, but we have to deal with this square root here. That's why it's called rationalizing. We're going to have to deal with this, break this up, in order to get our problem correct. So we're going to go down and say, okay, well, the limit as x approaches 0, okay, of this function up here. This is the same thing if we wrote square root of x plus 1 minus 1 over x. If we multiplied this by the conjugate of the numerator. Now, what the conjugate of the numerator is it's going to be the exact same expression, so x, square root of x plus 1, but instead of subtracting 1, we're going to add it. So this is a factoring technique called the difference of squares, and it's going to help us free up this square root. And we're going to divide by the same amount. So we haven't changed our expression or our function at all because we're multiplying by 1, because this is the same thing. So we are going to simplify this, and it's going to help us to find our answer. So the numerator, we need to FOIL. And when we FOIL, these are going to square, and these are going to square. Okay? They're going to multiply by each other. Now what's going to happen here is the outside and inside terms are going to cancel each other out. You're going to get a positive square root of x plus 1 and a negative. So the O and the I from FOIL are gone. So what you're left with on the numerator is just going to be the square root of x plus 1 squared minus 1 squared. And now this is a very important step right here. Don't multiply the denominators out. Just stack them next to each other. You'll see why this is important in just a minute. Now if I simplify my numerator, I'm going to get just x plus 1 minus 1 all over x times the square root of x plus 1 plus 1. The numerator simplifies to x. Well, just like in our dividing out problem that we did earlier, we've got the same factor in both numerator and denominator. That's why we end up with this, 0 over 0. So we are going to cancel these out, and you're going to be left with 1 over the square root of x plus 1 plus 1. Now, if we go back and we plug in our number 0 in, we're going to be left with 1 over the square root of 0 plus 1 plus 1, which should get us 1 over 2. So now we actually have our answer. But we had to do two things. We had to not only rationalize our function, but we then had to divide out what was left. Big key here, don't combine those together. Just keep them factored, keep them separate, and everything will work out nice and clean for us. When we go to our anytime where you have this situation where you're dividing by 0 again, you're going to look for some way to get out of it. With trig, regular algebra doesn't always work, so you're going to have to use your identities. In our concepts video, we showed that there are two main trig identities that you need to know, and they're listed right over here. So we're going to use these to our advantage. So again, if we start out, if we plug in 0, from earlier in the video we had the tangent of x, the tangent of 0 is 0. So if we plug these in, we're left with 0 over 0, which is the indeterminate form. So we've got to figure out a way to deal with this. We've got to use these to our advantage. Now, what I'm going to do here is I'm going to separate this function into all numerators and all denominators. Tangent is the same as the sine of x divided by the cosine of x. Okay? And we're multiplying by 1 over x. So that's where we're dividing by x, which is the same thing as multiplying by 1 over x. So this we can think about as the same thing as the sine of x over x times 1 over the cosine of x. So I've just reordered this a little bit. You see that when we multiply fractions, it's like having one big dividing line because you multiply straight across. So it doesn't matter if I switch the cosine and the x. It doesn't matter because as long as I'm still multiplying, I'm good to go. So now what I have are two identities that I have at the top that I can use to answer my question. So the limit as x approaches 0 of the sine of x, or excuse me, the tangent of x over x is the same thing as the limit as x approaches 0 of the sine of x over x multiplied by the limit as x approaches 0 of 1 over the cosine of x, which from our numbers up here is the same as 1 times 1, which gives me 1. So this may seem very complicated, and it's kind of a puzzle, which most of the time dealing with trig functions, they are kind of puzzles, but you've got to know when we see this 0 over 0 that more work has to be done. And when we deal with trig functions, you have to deal with them with these two identities. The last example that we're going to do is one where we've got to, again, think a little bit outside of the box and try to work this out the best we can. Here we have sine of 4x over x, which, again, if we plug these in, the sine of 4 times 0 is 0, divided by 0, and the sine of 0 is going to be 0. So, again, we have the indeterminate form, which means more work for us. Yay. So we need to rethink this. We can't use this for this yet, because I've got a 4x over x, not an x over x like it says. But we're going to get a little tricky here. Okay, so we're going to rewrite this. We're going to say, well, what if it was the sine of 4x over 4x? Which now these are the same. If those are the same, okay, then I can actually use this thing at the top. Don't worry so much the fact that these are x's and these are 4x's. As long as they're the same, this will hold, okay? Because again, x's are just unknowns. So if 4 times an unknown, and 4 times an unknown, it'll still be the same number. So how do I go from here to here? Well, what is it that I've exactly changed? All that I've done is now I have this 4 multiplied into my denominator. That's the same thing as dividing by 4. Okay, that's the same thing. So in order to balance this out, if I'm dividing by 4 here, in order to balance it back, I need to multiply by 4 on the outside. So here, these 4's cancel, and you can see that I'm back to what I had before. So what I'm going to do is just continue now. So the limit as x approaches 0 is going to be 4 times now the limit of this. Well, I told you before, this is the same thing as this up here. So I know that this is just 1. And so the limit of 4 times 1 is always just going to be 4. So this is our answer for this. Now these trig ones are a little trickier, but when we see that we have this 0 over 0, we know that we have to make these things work for us. Just like in the other examples. In this case, we got 0 over 0. We saw square root, so we know that we have to rationalize. In this case, we got 0 over 0. So we don't have square roots, we don't have trig, so we know that we need to divide out. So those are the tricks of the trade for dealing with analyzing limits.